Hi everyone, welcome to episode 4. So this will be discussing Newton's laws. Well, this is an episode on forces actually, which are Newton's laws. So this episode is on forces. Okay. Sorry, I'm just a little tired. Okay. Let me discuss the 3 laws first before we get started. So, Newton's first law is when you have a body in equilibrium, which is saying that the sum of the force is equal to 0. And this is first law. Now, in non-vector form, what this means is F is equal to system, which is equal to 0. That's what this means. This is an equilibrium problem, so this one applies to center of mass. So this applies to center of mass and rotation. So we'll really get into the first law at the end of this entire show. The second law is the sum of the force is equal to mass times acceleration. Now, they are laws of motion. So the first law is when you have like an equilibrium position where everything is balancing itself out. So you can imagine 2 things are going opposite from each other. They create stability. Or they're pointing the same direction in. This is the second law. And then this applies to waves on strings, which is sound. And then we could also say that the force is equal to a system that's equal to mass times acceleration, right? MA. And the system is a diagram. It's a free body diagram. And then the third equation is we say that the force 1 on 2 is equal to the negative force on 2 on 1. And there's no really other explanation for this one, but this one applies. This is third law. This applies to electric charges. This is an L, by the way. Electric charges, which is electricity. So this is what we're going to be talking about in season 2 is sound and electricity. Okay. That is the 3 laws you need to understand. As far as kinematic equations go, the formulas are not going to be important. Onward. The sketches, some of them they might be important. Okay. Let me go through a conceptual example. Like I said, we're going to tread lightly into forces. I'm not really going to do a problem about forces. I'd rather just explain the theory behind them. Okay. Other than that, and when we did kinematic equations, we didn't care about mass. In forces, we do consider mass, but we don't care about velocity because the velocity is constant. Other than that, velocity will matter when we get to circular motion. Like I said, circles are really the part that I want to stick out. So instead of doing forces, I'm going to do a surprise alternative. Instead. Trying to find this conceptual problem. Hold on. Okay, here it is. Net force and acceleration in free fall. So a object was dropped from rest from the Leaning Tower of Pisa, if you remember 1D kinematic equations. If the object falls freely so that the effects of the air are negligible, we're talking about air resistance. The effects of air resistance are negligible. How does the net force on the object vary as it falls? So in free fall, the acceleration of the object is constant and equal to the gravitation due acceleration. Okay. In free fall, the acceleration of the object is constant and equal to acceleration due by gravity, little g. Hence, by Newton's second law, the net force, sum of the force is equal to mass times acceleration, is also constant and equal to mg, which is mass times acceleration due to gravity. In other words, what they're saying is that you're taking this equation, the sum of the force is equal to mass times acceleration, but then we're rewriting this as the sum of the force in the y direction is equal to mg if we take a component, if we take a y component. Which is the object's weight. The object's velocity changes as it falls, but the net force acting on it is constant. If this surprises you, reread conceptual example, the other one. That's okay. The net force on a freely falling object is constant even if you instantaneously toss it upward. The force that your hand exerts on the object to toss it is constant force, and it disappears the instant the object leaves your hand. From then on, the only force acting on the object is its weight W. So you're going to have an object such as a disc, right? We can imagine some disc. This is a poor sketch. And then it could be a coin or whatever we want to think about it. And then it's going to have some weight to it, right? So we say the sum of the force is equal to W, weight. But we could just say mg, right? ma. Which I showed you what happens with the ma. This turns into f sub y was mg, right? The sum of the force in the y direction is equal to mg. That's what this equation also becomes. And then acceleration just turns into acceleration due to gravity because we're in the y direction. We only care about the y direction. Okay, this is a nice touch-up on the last one. Other than that, let's wrap up this section. This is a very quick explanation on forces. I want to go quick on forces because I want us to get into circular motion, but I'll have a surprise before we get into circular motion. I'm going to show you some like a little modern physics. A friend of mine asked me to do a video on quantum mechanics, and if he watches this show, he might get a little nice way of understanding quantum mechanics. Okay. So if you have a force on a vector, I must show you like Newtonian mechanics. We're going to do a little quantum mechanics as a surprise. So force as a vector. Force is a... Okay. Force on a vector. Sorry. Force on a vector, we call it R. R just means the total force, and we say it's equal to force 1 plus force 2 plus force 3 plus so on, which is equal to the sum of the force. Now, I did show you over here on the back how this applies to center of mass, right? You're going to see this kind of setup when we get into center of mass. I don't think we get into that till we get to linear momentum. So this week I'm going to try to do forces, energy, and linear momentum. But this episode is just on forces. Circular motion as well, but we did circular motion in the last episode. We got introduced into it during relative velocity. Okay, so what this diagram is trying to show you is that when you have a box, right, it's an object. See, in the last problem, we talked about particles. Now we just talk about objects. When we're in Newton's laws, we have to talk about objects. So if you're having an object, this is like a tug-of-war situation. Let's say it's being pulled. This is the force. Well, you don't need a vector because it's a component. So it's the force in the y direction, which they call this, actually, this is the force in the x direction. My bad. Let me redo this problem. Okay, so this equation, right? This is force in the x direction. And then this is force in the y direction. And then in between, we call that R. And if you notice, R kind of connects this and this. This isn't a really good picture. So let me see if I can do this better. I have to kind of draw it backwards. So if R, so we got to make the center of the box right here, right? So imagine we call this the force. Right, this is force in the y direction, and then we call this force in the x direction. And then the vector in between is the r. The vector between the two components, we call that the r, the total force. This is force. Force, you got force going this way. This is like a magnification. The y component this way, and then the x component in this direction. And then you're going to have some box, right? You're going to have a box here. Not a good drawing of a box, but you get the idea. It's going to be a box. All right, that's the first setup, first equation. And then next equation is we say the sum of the force is equal to 0, where 0 must be a vector, by the way. This is a ball, not a circle. It's a sphere. So you're going to have a force coming in this way. We call this F1. Since it's just a number, we call that a force, so that's force 1. And then this is where we get an equal and opposite reaction kind of occurring going on in this equation. So we say that force 2 is equal to negative force 1. Wherever there's a force, there's an equal and opposite reaction. There's also going to be a velocity, which is constant. Okay, velocity is constant. And since it's constant, we can ignore velocity. We don't need to worry about it. Other than that, this is where the sum of the force is equal to 0. Now, if you notice, this third equation here acts just like the first one, which is interesting. All right, that is that one. And then to do the next one, we say the sum of the force is equal to mass times acceleration. Sum of F sub x is equal to ma sub x. And then sum of the force sub y is equal to ma sub y. And then sum of the F sub Z is equal to MA sub Z. Okay. That is your components. So other than that, this one acts similar to this setup. It's the same principle as this one right here. So this is separated, by the way. And also this is too. What this is showing you is that when you have a box, which is an object, we can't use the word particle. We can't describe this as a particle. We must describe this as an object. There's going to be a force pulling on this object, right? You call this force 1. It's going in the horizontal direction, the x direction, or just call it the horizontal direction. And then you're going to have another force that's pulling in the vertical direction. Call this force 2. In between is the sum of the force. You notice how these two are similar. This is like the first, I think this is the first and the second, but they're all similar if you notice. These two diagrams are. And then you say that you can have acceleration perhaps going this way. Now I know these lines aren't really that straight, but now I just made it straight, so we're good. Acceleration is going this way, so then you say that acceleration is equal to the sum of the force over mass. Okay. So this is this part, right? This is this, and then this is all this. This is actually this whole thing right here. And then you get the whole system there. Okay. Alrighty. Other than that, if you do have, and I'm going to separate everything here. I don't want to make it all, I want to separate it to organize it. So the next one is if you have a ball, right? This is a sphere, and you're pointing downward. You're going to have a mass. We could put it in the center. This is a mass. It's got to have some weight. Well, it's mass. This means weight is equal to mass times acceleration due to gravity. And then right here, you're going to have, this is called acceleration due to gravity. All right. That is that part. Other than that, if you have a ball, and let's say it's being kicked, it's going to have force 1 on 2, and then it's going to experience a negative force 2 on 1. All right, that is all I should show you here. I guess the B means the ball, so that's a ball. I'll put the B in the center. B just means ball. Okay. Now, what really is important here that we're going to do problems with is going to be something with this diagram and this diagram. I'll show you the equation that works with this. This basically is just saying that the force 1 on 2 is equal to the negative force 2 on 1. That is the equation responsible for that. The equation responsible for this one is this equation. Other than that, just worry about the first one and the third one. It's important, too, that I showed you what they apply to. Okay. We are going to do network flow, but before I do that, let me discuss some interesting information. Okay. So, I don't know if you've heard of this book, but I actually do like this book. It's called The Dancing Wu Li Masters. Now, the words Wu Li has many meanings, and it means patterns of organic energy. So when I talked about the kinematic equations and how they relate to each equation, You could think of that as a pattern of organic energy. And what makes it organic is that we're taking nature. Nature is an organic compound. It's an organic structure. I mean, I don't really think there is such a thing as inorganic chemistry, because any kind of matter has to be organic. I mean, everything is organic if it's made from the universe. So I don't think there's such a thing as inorganic. I don't think it exists. Everything's organic. Okay. Enough said of that. There's another book that acts as its predecessor. So you're going to have the Dancing Woolly Masters. I recommend you read this book. You'll learn about photons. Now, this book is not written by a physicist. It's written by a spiritualist. And it's a Zen book on physics that's made for people who have a hard time with physics. Read this book. It's really interesting. It's all about light. So it's pretty much the whole theme of this book is about photons. There is a volume 2 to this book. There's a second book that kind of continues the story out. And it's called The Tao of Physics. Read this one as well. This was written by Fritjof Capra, who is a physicist, not a theoretical physicist. He's an experimental and a theoretical physicist. He's both. And the word Tao means way. This is a very interesting book. It's basically what it's about is in the Western world, when you learn physics, right? Everything started from Greece. Everything was pretty much philosophy in the beginning, and physics had a very stationary perspective. When you study a lot of Western religion, whether it's the Bible, the Hebrew book, the Quran, any Western religious book will always mention of things that are stationary and fixed. Now, what's very interesting is whenever you read the Bible, you're not going to really hear about motion or change. So, and that's because the Western thinkers do not want to think like that. In the old physics, when we talk about Newtonian mechanics, it works nicely. Classical mechanics, it works well with the Western core beliefs. The Eastern world is the opposite. It's more about motion and change, and things never stay still. So, like in Taoism, for example, we'll get into Taoism when we get into energy, but I don't want to get too extreme with it. But the idea too with Taoism, and it's kind of like this last equation with equal and opposite reactions. It's kind of, think of it as like a balance, like a scale. Best way to think about this kind of stuff with Newton's equations, Newton's laws, is to think of them like a scale. So imagine if you have something that's pointing in both parts are pointing in the positive direction. You're not going to have anything negative. It would be chaotic, because it would have too much positive chi, positive flow of energy. Well, let's just say positive flow. It would have too much positive force acting on a system in nature, so it would be chaotic, if you think about it. Anything that points in the negative direction would also be chaotic. So what the Taoists would say is you would have to like balance it by pointing it in both opposite directions. And what's interesting too in ancient Japan is they had this belief. So the emperor of Japan was like their yang. It was their positive force. And then their samurai was like their yin. It was their negative force. So they believed that having a balance between positive and negative basically created peace. Create a peaceful system. And it's very interesting to apply this. Now, I don't want to go too deep into this, but this is a very interesting book. So it talks about how modern physics acts more like Eastern mysticism. So like in Hinduism, they believe in the cosmological dance. So they believe in the sounds of the universe, how the drumming in their music represents how the universe is constantly dancing and moving. I mean, that's their whole religion. They think the music is that. In Taoism, they'll talk about energy. We'll get into energy and when we get into energy. But forces are like energy. Whenever there's a force, whenever there's work of force being done onto the system, there's energy responsible happening. We will talk about that as well when we get into energy. For now, don't worry about energy. We only care about forces. Forces is what we want to study. That's the whole point of this episode, is forces. So I have to kind of explain energy, but we're only going to lightly we're only going to touch energy. We're not really going to get into energy. So I'd rather explain forces. Other than that, check these books out. They're awesome. Sorry about that. My phone fell. Almost did. All right. Okay. Let's continue. Now, pay attention to this problem right here I showed you. You notice that there's an object, but something is coming out over here. Something is also coming out on the other side. You could say the same thing with this. An object, there's something coming in, something coming in, something coming out. I don't know why this phone won't stay in the proper location here. This is not a very good tripod. All right, just think of it like that. It's a good habit. Oh, we got to go back to this book. Okay. Basically, with this book is Heisenberg planted the seed for this book. This guy actually met Heisenberg in the early 70s, in the early 1970s. And Heisenberg created the idea with this book. You have to read it to understand, but he planted the seed that created this whole book of how it was written, the Tao of Physics. So in English, it means the way of physics. An exploration of the parallels between modern physics and Eastern mysticism. Now, Heisenberg is a very interesting physicist that I should mention. He came up with two concepts. One is called the uncertainty principle. We kind of did that in classical mechanics. So I'm gonna sketch out an example of what is the uncertainty principle. Imagine there's a road, right? Imagine there's a road. Now, it can mean anything. An uncertainty principle to a carpenter could mean that if he has a counter and he has to measure, how would you measure an area of a counter? You'd have to take length, or I have an idea. Uncertainty principle is like taking the dimensions of the sheet of paper, right? We have this single sheet of paper, but we want to measure its dimensions. We're going to have a human error. So how do we get an error? How do we get surface area of this paper? We'd have to measure the length. Then we'd have to measure the width, multiply it by 2, because you have length. Actually, no. You take the measure of the length, measure the width, multiply it. That would give you your surface area. But each measurement is going to have an uncertainty. So if I have a ruler, there's going to be so many lines that it's going to be able to see because of human error. Don't have a ruler on with me. I'm gonna get a ruler. Right. Just hold on. I'm gonna get a ruler. I actually don't have a ruler. I'm surprised. So in a ruler, you're going to have, I'll sketch a ruler out. So in a ruler, you're going to have lines, right? You have little lines in between that measure a ruler, right? They look something like this. Well, each of these lines have a specific distance, right? They have a little delta x, but really it's not a delta x, it's a differential, so we can call it dx. But they're only going to be measured for how many lines there are. We're not going to know, like, past that measurement point of reference. So the idea with this paper is if I measure the length of this paper and I measure the width, there's going to be human error on each side, which is going to give me an error measure. Okay, that is the classical notion of uncertainty principle. Now, to look into the quantum world, imagine that I go down, a car is coming down a road that's 50 miles per hour, and let's say the road is shaped like this, right? And the road kind of has an intersection like right here, and like right here. Now this road is 3 miles long, right? Well, in quantum mechanics, we don't need to care about the distance. So this stretch of road is 3 miles long, but then there's going to be little intersections here and here. You want to ask yourself, how would you take the position and the amount of time it's coming? You would have to take what's called a time derivative, if you remember. And remember that the time derivative gave us our slope, which we said the time derivative of distance is velocity. The time derivative of velocity is acceleration. Quantum mechanics is not as simple as that. So if you know the position, right? You're not going to know any of this road map. So like if you know the position, it could come in this way, it could come in this way, it can come in any direction, and we wouldn't know which way it's coming in. This is how crazy quantum mechanics is. It could sink from anywhere. It could come in from any direction, which means it could go out in any direction. So this is insane. Like, this is how quantum mechanics can get difficult. And then the other issue is if we know the path of this, we don't know where it's going to stop at a certain time. So it could be here, 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 it could be here. This is how difficult quantum mechanics will be. So that's the uncertainty principle, is we will not know the position. We won't know the position if we know the path, but if we know the path, we will not know the position in the point in time. And we can think about this as momentum. Now, I know we're not doing momentum yet, but this is an interesting application. So we're going to do a problem. We're actually going to do linear algebra is what I plan on doing. And we're going to pick a problem from here. I kind of thought about this, and this is really cool. Oh, let me show you what I'm talking about here before we get into that. So when you have the uncertainty principle, it led into a second concept that was called the scattering matrix. And it is the S matrix. I'm going to write it out. Because you ask somebody if they ever heard of the scattering matrix. They're not even going to tell you what it is. But I will tell you what it is on this video. We're not going to do a problem on how to solve it because you have to use complex analysis, and I haven't taken that course. So I don't understand what it's going, how to explain the math for it. I'm going to show you a scattering matrix problem. So, a very simple way of knowing the scattering matrix is if you have what's called a reaction channel. So you're going to have a path of a particle that comes in. Imagine there's two particles that come in different directions, right? We talked about particles in the last episode. It's going to come out this way, and it's going to also come out this way. Basically, the way this is if you know the path this is going to be like a reaction. Like we call this a reaction chamber. It's kind of like if you see the similarity, it's just like this example here. Wherever there's an action, there's an equal and opposite reaction. You can consider this like a reaction. It's kind of like if you have a chemical reaction. So that is the scattering matrix. You can get problems much more complicated than this. So you could get something that looks like this. It can get harder. I mean, these diagrams are a little off, but okay. You can have something that looks like this. Oh, they can get harder than that. I mean, that's just basic. They can get more complicated. So you could have something that looks like this. These are separate, by the way. They don't really intersect. They only intersect where the circles are. I screwed up this drawing here. This drawing should have been this. Alright, if you ask an astrophysicist, they're not going to know what these are, but if you ask a particle physicist or a nuclear physicist, they'll know the scattering matrix. I got to make the next diagram smaller. What I was trying to draw you was this. See, they just keep branching, basically. That's how this works. And then you got something like that. Alright, that is the scattering matrix. You notice each time it hits a collision, it branches off. And that's the important part. And like I said, it can get harder and harder. These drawings can get more and more complicated, so you could have something like this. Kind of looks like molecular structures if you think about like organic chemistry. Or I guess it's my way or the highway. It's a joke. Okay. Scattering matrix. Also, I didn't show you an equation for kinematics. There's a space-time equation I'd like to show you from the book. When we did kinematic equations the other day, so if you want to do space-time, right, you got R UV is minus 1/2 G mu V, I think that is a V, right, times R, which is equal to K T sub mu V, and that's space-time. That's if you're in a this is for 4D. So if you're in 4D, you use the space-time equation. You know what? I'm going to make this into another episode. I'm going to probably upload this first before I explain the other one. Forget about the space-time. I'll explain. I'll put a minute video explaining what 4D would look like, because I feel like 4D will be mentioned. All right, just scratch that off. We're going to start network flow, but before I do that, believe me, we're not going to do a quantum mechanics problem. This is, the way I'm going to do this is we're going to use a linear algebra problem. Because then we'd have to use complex. If I actually had to show you this problem, I'd have to use complex analysis. The only way you can explain that is a matrix. I mean, it's the scattering matrix. But let me show you what this applies to. So really, the key here is something that looks like these two simple diagrams. Don't worry about this one. It's kind of like these two. So I'm going to do a problem. So if you have network flow, right? It's the same thing I just showed you. Call this 30. We're going to give it numbers. And then this is point A. Comes out to 80. And then goes downward. We call this X1. Another point. 60. Comes in. These are arrows, by the way. And then this is called point E, which comes out to 20. And then we call this X3. Point B. X2. Oh, this doesn't exist, by the way. This, I'm going to resketch this. I screwed it up. $30, 80, X1, E, 60, call this B, X3, X2, and then X5, X4, D, straight line, X6, C, and then this turns into 40, and then 100, 90. And then you have 40 going in. Okay. This is what we call network flow. So 80, here, the idea with network flow, oh, I forgot to do the 20. 20 is coming out. This is what they call junction rule, which comes from Kirchhoff's rule. When you do circuits, you're going to be doing problems like these. So the idea is you got to look at the junction points, right? We look at this junction point. We look at this junction point. It's kind of like, imagine a reaction channel. We look at this junction point, we look at this junction point, and we look at this junction point. There's going to be 5 junction points. So 30 is coming, at junction point 1, 30 is coming in, 80 is coming out, x1 is going out, x2 is going out. That's this junction. This is what they call mapping. Junction 2 is 60 is coming in, 20 is coming out, x3 is coming out. Okay, and then this junction, we say that x3 is coming in, x2 is coming in, x3 is coming in, x4 is coming out, x5 is coming in. And then this junction, we say x5 is coming out, 40 is coming out, 100 is going in. And like I said, this is junction A, junction E, junction B, junction C, and junction D. So junction A, right, 30 is coming in, 80 is coming out, x1 is coming out, x2 is coming out. Junction B, x3 is coming in, x2 is coming in, x3 is coming in, x4 is coming out, x5 is coming in, and then junction C is we say that 40 is coming out, x5 is coming out, 100 is coming in, right? 100 is coming in, and then junction D is we say that an x6 is coming in, right? So junction C, we say that x5 is coming out, x5 is coming out, 40 is coming out, 100 is coming in, x6 is coming in, and then junction D, we say that B is coming in. No, junction D, x4 is coming in, x6 is coming out, 90 is coming out, 40 is coming in. Okay. All right, it's hard to switch between math and physics. All right, let me show you how to solve this problem. What did I do with that? Still here, guys. Okay. All right, so you have to write down the equations for each junction. That's what you got to do. Okay. So we got to write for each junction. So for A, we have to say that 30 plus x2 is equal to 30 plus x2 is equal to 80 plus x1. And then B, it's junction A, now we're in junction B. So you have to basically say that you got to call this flow in is equal to flow out. It's like flux. The word flux means flow. B is x3 plus x5 is equal to x2 plus x4. C is x6 plus 100 is equal to x5 plus 40. And then D, we'll just do colons for each one. So D is x4 plus 40 is equal to x6 plus 90. All right, ignore all this might be important. And then E is x1 plus 60 is equal to x3 plus 20. Okay. And then in addition, we have the relation that the total in equal the total out. So if you add up all the numbers, you're going to have 60 plus 40 plus 100 plus 30 is equal to 80 plus 20 plus 90 plus 40. Okay. And then this relation is satisfied. Since it has no variables that can be omitted, we write the equation for junctions in the standard form. And then you'll have x1 minus x2 is equal to 50. This is systems of linear equations. x2 minus x3 plus x4 minus x5 is equal to 0. And then x5 minus x6 is equal to 60. And then x4 minus x6 is equal to 40. And no, this one's wrong. x4 minus x6 is equal to 50. And then x1 minus x3 is equal to 40. Negative 40. Okay. And then basically, if you want to put it in a matrix, you're going to get something that looks like this. You're going to get 1, 0, 0, 0, 1, negative 1, 1, 0, 0, 0, 0, negative 1, 0, 0, negative 1. Zero, 1, 0, 1, 0. Zero, 1. 0, negative 1, 1, 0, 0. 0, 0, negative 1, negative 1, 0. And then if you want, you could put like a line in between. On the side, you're going to have negative 50. Basically, it's all these equations. It's just a variable expression. So if you, where these numbers came from is just the 1 minus 2. You see it's positive, negative, positive, negative, positive, negative, and then wherever there's no variables listed, you just put a 0. You go by the bases. You notice that you follow the subscripts. So the subscripts represent the columns. 1 is column 1. 2 is column 2, 3, 4. How it works at the bases is you got 1, 2, 3, 4, 5, 6. That's linear algebra. Okay, so negative 50, 0, 60, 50, negative 40. Basically what this line means, this is like an equal representation. That's what this means. That means equal. Okay, so if you wanted to row reduce it, you can use a calculator. You're going to get, this simple means row reduction. This will become this. So you get 1, 0, 0, 0, 0. Wait, I didn't reduce it, did I? Yeah, 0, 1. I reduced it. 0, 1, 0, 0, 0. Negative 1, negative 1. 0, 0, 0. 0, 0. 1, 0, 0. And then 0, 0, 0, 1, 0. 0, 0, negative 1, negative 1, 0. Okay, and then this is like the equal sign, so you're going to have negative 40, 10, 50, 60, and 0. And that's when you reduce this. You have to hit the button in the calculator. I think that's what you do here. Try it. I'm going to show you how to do it. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Let's try it. Come on. It's taking forever. Okay. Menu 711. Actually, it's going to be 1, 2, 3, 4, 5, 6, 7. I did that backwards. It's 5 by 7. Right. 1. All right. Yep, see that? When I reduce it, it matches my answer. Notice the coefficients are all the same. I get negative 40, 10, 50, 60, 0. This is basically row reduction, is what this is. This is from chapter 1. This is applications. This is systems of linear equations, but this is linear algebra. I just wanted to show you how to do some linear algebra here. Okay. So now you learned something new. This is like a way to tackle the scattering matrix. Other than that, this is like what you want to do is use a matrix. Other than that, to actually do a scattering matrix problem, like based on linear algebra, you would know how to solve it once it's set up. It's just setting it up is the hardest part. Okay. Just thought that would be interesting. Okay. Let's continue forces. So, there is one more chapter that I have to get through. Probably just going to go straight into explain just everything in a nutshell. Okay, this is where it gets funny. So when you have forces, you're going to have conservative and non-conservative forces, which is pretty funny. It's kind of like liberal in, it's kind of like thinking like conservative and non-conservative parties. I wouldn't say the word liberal, sorry. It's like having like conservative and non-conservative. So anything that's non-conservative gets lost in the system forever. Other than that, anything that's conservative, you can get it back. It's pretty funny because it's like politics a little bit. So, forget I said the word liberal. Just cancel that out. Other than that, conservative is like you're going to get it back no matter what. Non-conservative, conservative, you're always going to get it back. Non-conservative, you won't. So the way conservative works is like, imagine that there's some crazy looking path like we did before. Conservative is just like, okay, I only need to know the initial point and the final point. I don't care what happens in between. Non-conservative cares about what happens between. But anything that happens in between gets lost. It gets lost in the universe. That's really the difference between conservative and non-conservative. So, I just thought that was funny to explain. Other than that, that's all you really need to know. Let me do the vectors. So, I showed you the part where the vectors, right? Actually, what I'm going to do is pull this up. So, you have the sum of the forces equal to mass times... Oh, it doesn't show you equilibrium. I'll show you equilibrium. Okay, so if you have an equilibrium problem, you're going to say the sum of the force is equal to 0. Force in the x is equal to 0. Force in the y is equal to 0. And this is if you're in component form. So you got vector form, component form. Basically what this set means is if you have like a block, they always say the angle is being taken from the x direction. I always like to say the angle is from the y direction, and believe me, it is. You're going to have some block that you take the center of mass. So it's always going to have mg at the bottom. It's always going to have a weight vector, which we know that weight is equal to mg, right? This is weight is equal to mass times acceleration due to gravity. And then the normal force, which we can call it the little n, right? That's the normal force. And then tension is coming this way. All right. And then if we look at the components of this, if we want to magnify it, we imagine that there's like a center of mass happening right here. Right? You got the tension. Got the tension, T. By the way, T does not mean period. It means tension. It doesn't mean tangent either. It means tension. Okay, so tension. And then you got normal. And the normal is going to be in the y direction. This is like your Cartesian system that I showed you before. The acceleration is w cos alpha, right? And then, I guess they use like a little wiggly line. They use like a big wiggly line, like a big S or something. And then the distance here, we call this the angle, we call this the alpha. The alpha is the angle between. And then here, this is just an x. So you have an x and a y. Okay. And then the second part, when you take the sum of the force is equal to mass times acceleration, right? We say the sum of the force is equal to mass times acceleration. And then if you want to put it in component form, you say the sum of the force in the x direction is equal to ma sub x. Sum of the force in the y direction is equal to ma sub y, right? Basically what you're going to do is you're going to take the same diagram here. I'm not going to resketch it because it's the same thing almost. All you have to do here is add in an acceleration vector, which means you're going to add in an acceleration component. All right. And then when you have friction, friction is actually non-conservative. It's actually gets lost in the system forever. There's two types of friction. There's static friction and kinetic friction. So like Static friction is what keeps an object from moving. So like if I put this pen down and it doesn't move, or this calculator, right, doesn't move, that's static friction. That's what keeps it stationary. Kinetic friction is when you have something sliding down and like, so like if I slant a book, right, where this pen, well, that would be rolling motion. I'm trying to explain. If I slide this calculator from a book, we'll call this like the kinetic friction. So like the fact that that can slide is kinetic friction. So like if I could do that, that's called kinetic friction. If I could slide the book across the table. Other than that, that's really all that is. Kinetic friction is the F sub k is equal to mu sub k times n. Now n is the normal force. N is the normal force. And then if we're in static friction, then we say F sub s, it has to be less than or equal to mu sub Sn. All right, and that's it. Other than that, in the end, we'll do acceleration in uniform circular motion. So if you have acceleration, you're going to have the radial acceleration is equal to v squared over r, which is then equal to 4 pi squared r divided by t squared. Okay. And then if you take a circle, you're going to have this. You're going to have velocity pointing this, the velocity vector pointing outward, the acceleration. Well, the sum of the force is going to point this way. And then the radial acceleration is pointing in the same direction. So this is like taking it a step further. And then you take another point where the velocity vector is over here. The sum of the force is also pointing inward. And then the acceleration vector points, radial acceleration points in the same direction. And then if we take one more, we say the velocity is pointing outward. The sum of the force is pointing inward. And then radial acceleration is pointing inward as well. So this is just a step further what we learned in the last unit. I'm going to blow up this circle because this is really hard to read. We'll do 3 points, right? So what this is showing you is that if you have velocity vectors, right? You're going to have velocity vectors pointing out. And then you're going to have, instead of repeating it, I'm just going to show you. So you're going to have the sum of the force pointing inward. And then your radial accelerations are just going to point in the same direction. That's all this is showing you. Okay, that's about it. Other than that, let me read you the fundamental forces of nature, and then we'll do, should we do a circular motion problem? I feel like we should. And we're going to skip that. We're going to skip that tonight. We're not going to do one. Too much. All right, so the fundamental forces of nature, this is where it gets important. Okay, so gravitational interactions include the familiar force of your weight, which results from the Earth's gravitational attraction acting on you. The mutual gravitational attraction of various parts of the Earth for each other holds our planet together. Newton recognized that the sun's gravitational attraction for the Earth keeps the Earth in its nearly circular orbit around the sun. The second familiar class of forces, electromagnetic interactions, includes electric and magnetic forces. If you run a comb through your hair, the comb ends up with an electric charge. You can use the electric force exerted by this charge to pick up bits of paper. All atoms contain positive and negative electric charge, so atoms and molecules can exert electric forces on one another. Contact forces, including the normal force, friction, and fluid resistance, are the combination of all such forces exerted on the atoms of a body by atoms in its surroundings. Magnetic forces, such as those between magnets or between a magnet and a piece of iron, are actually the result of electric charges in motion. For example, an electromagnet causes magnetic interactions because electric charges move through its wires. We will study on the atomic or molecular scale, gravitational forces play no role because electric forces are enormously stronger. The electrical repulsion between two protons is stronger than their gravitational attraction by a factor of about 10 to the 35, but in bodies of astronomical size, positive and negative charges are usually present in nearly equal amounts, and the resulting electric interactions nearly cancel out. Gravitational interactions are thus the dominant influence in the motion of planets and in the internal structure of stars. The two classes of interactions are less familiar. One, the strong interaction is responsible for holding the nucleus of an atom together. Nuclei contain electrically neutral neutrons and positively charged protons. The electric charge between charged protons tries to push them apart. The strong attractive force between nuclear particles counteracts this repulsion and makes the nucleus stable. In this context, the strong interaction is also called the strong nuclear force. It has much shorter range than electrical interactions, but within its range it is much stronger. The strong interaction plays a key role in thermonuclear reactions that take place at the sun's core and generate the sun's heat and light. Finally, there is the weak interaction. Its range is so short that it plays a role only on the scale of the nucleus or smaller. The weak interaction is responsible for a common form of radioactivity called beta decay, in which a neutron in a radioactive nucleus is transformed into a proton while ejecting an electron and a nearly massless particle called an antineutrino. The weak interaction between the antineutrino and ordinary matter is so feeble that an antineutrino could easily penetrate a wall of lead 1,000,000 kilometers thick, yet when a giant star undergoes a cataclysmic explosion called a supernova, most of the energy is released by way of the weak interaction. Wow. In the 1960s, physicists developed a theory that described the electromagnetic and weak interactions as aspect of a single electro-weak interaction. This theory has passed every experimental test to which it has been put. Encouraged by this success, physicists have made similar attempts to describe the strong electromagnetic and weak interactions in terms of a single grand unified theory, GUT, and have taken steps toward a possible unification of all interactions into a theory of everything, TOE. Such theories are still speculative, and there are many unanswered questions in this very active field of current research. Okay. This has been a great episode. Just stay tuned, and we will get into black holes. I made a little mistake on the liberal word. I was thinking of something else, but it has nothing to do with this. Other than that, this has been a great episode. The next one will be on energy, which is going to be also interesting. All right, thanks.